Okay, so let's get going. Welcome to today's CEA Power Hour, titled Digital Displacement. We've got two really excellent speakers today from Danfoss, and I'm just going to run through the opening bit before I hand you over to our technical expert. I'm Joanna Oliver. I think most of you know me. I'm Director of Global Programmes for the CEA and have been for about 100 years. I look after all our international programme and also external affairs and conferences. Quickly, the rules of the CEA House. The webinar is held in accordance with the CEA corporate compliance rules, which is really important. We don't discuss anything that's antitrust, anti-competitive. The webinar is being recorded and will be made available on our website. So if you don't want to be recorded, either leave now or don't say anything. Please stay on mute unless you are asking a question, and please do use the Zoom chat box to ask your questions in advance. We'd really like to hear from everybody. There's quite often a deathly hush when we ask for questions, so particularly today the guys from Danfoss really would like some input from the audience. Please turn off your video. I know some of you don't have the greatest connections, so you will get better reception if you turn off your video. And we always do our best to make the technology work, but don't shout at us if it falls over. Okay, so I'm now going to hand over to Dale Campsell, who's our Senior Technical Consultant. What Dale doesn't know about our industry isn't worth knowing, and he will be introducing the speakers. So over to you, Dale.
Thank you, Joanna. Good afternoon, everybody. Yeah, we've got an interesting discussion this afternoon. Just sort of taking a step back and putting it in context, air quality has been a matter of increasing interest globally, and in particular, CO2 emissions, and CEA recognises that we have our role to play. We have a part to play in finding a solution, and to date, we've looked at, in a previous session, I think it was back in March, one part of that solution could be in moving away from traditional power sources and looking at low carbon emitting power sources for our machinery. And that's a very active aspect of our role, but it's not the only one. There are other factors that will play a very important part in our sector, playing its part in achieving better and lower CO2 emissions. And some of that is to use the power you are generating in a more efficient manner. CO2 emissions are related to the amount of work a machine is doing, and if it can use that energy more efficiently, then the CO2 emissions will be less. So although the greater focus in recent times has been on the power source itself, that is only part of the solution, and probably only for part of the sector anyway. Yeah, it's with great interest I'm introducing the two Danfoss guys today, who are going to talk you through one aspect of that solution. So we have Niall Caldwell and Markus Plaßmann. So Niall joined Artemis Intelligent Power, which was the pioneer of digital displacement technology, in 1999. He became the managing director in 2013 and held that post until Danfoss fully acquired Artemis quite recently in February this year. He's now the Senior Director of R&D at Danfoss Digital Displacement, where he leads a 20-strong team of innovators developing the next generation of digital hydraulic machines and systems. At a personal level, he's an inventor of more than 60 patent families and joint winner of the 2015 McRobert Award, the UK's premier award for engineering innovation. And he's joined today by Markus Plaßmann. Markus has been with Danfoss for around 10 years. He leads the product management of their electrification portfolio. He's experienced in hydraulic closed circuit propelled systems, application software for mobile work machines, electrifying mobile work machines, marine vessels, and on-highway vehicles. His experience in R&D includes software development and product management, so a broad range of experience and expertise from both guys. So that's enough from me, and I would like to now hand over to Niall.
Okay, yeah, thank you very much for that introduction, very kind. So great to have you here today with us, and we're going to take you through a story that really starts at the beginning with the big picture. So let me share my slides now, if that is technically possible. We have practiced this, so this should work. Okay, so here we go. So we start with the big picture, and really looking at the Earth from space, we think about the challenges facing us. And really the big challenge we have in front of us today is to stop this beautiful blue thing from looking like this dead grey thing. And of course, CO2 is accumulating. Man-made CO2 is a huge challenge, and that is, if anything, accelerating. Now, sometimes it's tempting to think that these type of things, we just need to cut down, you know, it will stabilize. In fact, CO2, when we emit it to the atmosphere, it takes about 200 years to be absorbed in any meaningful amount by the sea, and then that takes a further 10,000 years to turn to rock. So if you look on the right, this is a simulation of what happens when we emit a pulse of CO2 into the atmosphere. And it takes around about 200 years for any of it to decay. So the conclusion from this, CO2 is not going to decay naturally in our lifetimes. It's simply going to accumulate. And it's a matter of time. So it's not just about how much we're emitting, but it's also how long we emit that for. So that really brings forward the urgency, the need to take urgent action, and the reason why this presentation we're focusing on what we can do to 2030. So as we see it, to avoid CO2 emissions accumulating into the atmosphere, we need a technology with highly effective emission reduction. We need that to penetrate the market to a significant penetration, and we need that to happen as soon as possible. So those are the three elements of the equation, if you like, we need to get right. It's not enough just to have an expensive technology that's highly effective, but it's over the horizon, or it's never going to be commercially viable. We need to get all elements of this equation right to make a big impact. Okay, so what is the total problem we're dealing with in construction machinery? Well, it's, according to Danfoss internal calculations, about 400 megatons of CO2 emitted globally. And of course, that's going up as the construction industry develops and compound annual growth rate and so on, the economy develops, that's only going to rise. In terms of where we put our focus when we're thinking about what to do, this pie chart is a bit of an indicator. And for digital displacement, it's really focused us on Excavator. As responsible, the one application that's responsible on its own for 50% of those emissions. So we've been talking in the last 6 months with some construction companies, some operators of fleets of excavators. And this is the sort of comments that we're getting back. They're making their own targets to reduce equipment, for instance, 40% by 2030, but they don't know how to do it. They're being asked by some customers to produce bids with zero emission machines, but they simply can't get hold of the equipment. They're trying to procure less emitting equipment, but they're finding that the options that are out there are just not there. On the other hand, the OEMs, many OEMs have committed, this is just a sample, and I think it's actually becoming a pattern across the board. OEMs are committing to science-based targets for the in-use emissions of the equipment that they manufacture. And here's a sample of the sort of targets, typically looking at 2030 as a milestone and making some stretching targets for there. So what's the solution? Well, the one that trips off the tongue and everybody maybe commonly assumes is the easy solution. Let's just make them electric. We have green energy, offshore wind, maybe for the UK. We use that to charge batteries, and we operate that green excavator using battery-powered, battery-stored green energy. So, yeah, sounds easy. But when we compare the challenge of electrifying, let's say, a 20-ton excavator with a typical family car, we see that it's not going to be as easy as many people think. So the excavator, has a similar power plant capacity to the car, but it's got a much more demanding system. It does much more demanding actuators. And those actuators work an awful lot harder. So the fraction of full power that an excavator tends to work on is much, much higher than a family car, which is basically producing only 5 to 6% of its rated power on an average duty cycle. The excavator, by contrast, is typically consuming 60%. So it's a very hard working machine. And of course, it tends to work for much longer. And as a result of that, you multiply these things together. An excavator needs an absolutely massive battery. And that battery can be so expensive that it's more costly than the rest of the whole machine. And finally, it lives in this tough environment with poor charging infrastructure. And that's a huge limitation in many job sites. There just isn't the electrical supply to charge these huge batteries overnight, especially because one of the first jobs of the excavator when it gets to the site is dig a trench for the electrical supply. So the excavator is really much more difficult to electrify than a family car. We could also ask the question, do we have enough green energy already? Of course, it's a nonsense to charge a battery-powered excavator from fossil-fueled generated electricity. So that will be a limiting factor. And we can do some quick calculations to see if we're in the right ballpark there. So we have roughly 1 million worldwide excavators in the field. When they're working, take about 70 kilowatts that they'll need to consume, working, let's say, for 1,500 hours per year. That gives us a total figure, 105 terawatt hours. So let's see what's available from offshore wind. There's about 29 gigawatt world capacity for offshore wind. It works at this 40% capacity factor, 24 hours a day, 365 days a year. And the result is about the same. So the shocking figure is that if all the world's excavators were 100% electric, they would consume as much electricity as generated by the world's current offshore wind capacity. So there are significant barriers to saving CO2 with battery electric excavators. One is the cost and supply of batteries, which of course will be competing with all the other consumers of batteries in on-road and stationary applications. The second is that lack of charging infrastructure where the excavators are actually used and stored overnight. And lastly, the limited green energy on the grid, which means that the growth of green energy powered electrified excavators will be limited by many other limiting factors with politics and with government intervention to stimulate the growth of green energy. So there are real significant barriers to that electrification. But to get a hint of what we can do, this is not a message of despair, but in actual fact, there is a hint of what we can do, and it comes by looking at where the energy goes. So let's look at the efficiency of transmission of the energy from that wind turbine to the end use. So, wind turbine generates power that's then transmitted through the grid fairly efficiently to charge batteries. Those batteries can then drive electric motors very efficient, and those electric motors themselves are very efficient. So far we have a very efficient transmission. And then when we look at the city car, we have just a very efficient transmission coupling that electric motor directly to the wheels. And so overall, the city car is a very efficient way of coupling offshore wind energy into driving the wheels of a vehicle. But when we look at the excavator, it's rather different. Excavator hydraulic systems today, the shocking truth is that they're only 70% efficient. Sorry, 30% efficient. 70% of the energy, useful energy generated by either the engine or the electric motor, 70% of that useful energy ends up as heat. And of course, heat you have to pay to get rid of. So this is a shocking fact. We could electrify all the world's excavators, but 70% of the useful power that we put in, that very expensive and you could say valuable green energy, 70% of that will be wasted as unwanted heat. And why is that the case? Well, it's to do with poor component efficiency in the hydraulic system, poor system efficiency, how the system is laid out and how it's controlled, and the fact that energy which could be recovered is not recovered. In fact, it's wasted and turned into heat. So although it sounds like bad news, in fact, it's good news. There's an opportunity here. There's plenty of room to save a lot of CO2 by improving that efficiency, but there's also a huge amount of cost opportunity. We've got $21 billion per year of wasted fuel, useful energy that's turned into heat that could be conserved. And yeah, we've been doing some communications this year, and in a recent event, we asked the audience, how is the interest in the topic of hydraulic system efficiency? And we were really surprised that 40% say it's strongly increasing, the other 40% say it's moderately increasing. So this is really a trending topic in the industry as more and more OEMs look to electrify and realize that it's the system efficiency that's one of the biggest blockages here. And indeed in the UK, as the threat of the diesel price increasing to the average operator. So we could look at some solutions. And of course, everybody's thinking electric, so maybe the obvious solution is let's just go completely electric. And here's some sort of groundbreaking demonstrations that have been done in the last few years using electromechanical actuators. So typically an electric motor, a ball screw or other mechanical mechanism that moves the actuator instead of using any hydraulic fluid. Now, I mean, the positives of these, the systems can be much more efficient. And of course, you get the electrified digital control benefit, so you can easily automate and have a better control experience for the operator. But there's negatives. Significantly, you can see on these drawings, on these photographs, these are very small machines, and already the actuators are huge and much bigger than the hydraulic cylinders that they would replace. But also the cost of these systems tends to be prohibitive. There's questions about scalability. These demonstrations have been done in the sort of 2-ton, maybe 3-ton range. Will it scale up to 20, 30, 40, 50 tons that we need for these large excavators? And then there's fundamental questions about the lifetime of these actuators, especially in the tough environment of an off-road machine. So there's another option which some are looking at, which is we call decentralized hydraulics. So we say, okay, let's stick with the hydraulic actuator we know and love. It's very robust, it's very power dense, it's actually quite low cost, but let's improve the hydraulic system that feeds fluid to those actuators. And so here's one idea that's been worked on, decentralized hydraulics, where instead of having one pump and valves which control the flow to the actuators, instead of that, you have multiple pumps, each of them fed with their own variable speed electric machine, and you connect them in a DC bus and supply those from the battery. Now, the positives of this sort of system, you can improve the efficiency of the system. You reduce the losses in control valves, so overall the system becomes much more efficient, and you can recover energy from the system. But there are some negatives here as well. You've got multiple high power systems, because at any one time, all the power could be going to one actuator. So you actually need a large installed capacity total power. System cost and packaging is also a concern with these systems, and scalability also is in common with electromechanical systems another concern. But the last one I think is worth focusing on. What we're talking about here is saying that the electric machines will not share their DNA with the diesel machines. And so we're saying that the manufacturers will be investing into a completely different technology path. And the question is, do we leave diesel machines behind? What if the diesel machines are actually 95% of the market and therefore 95% of the emissions? Are we improving enough by focusing just on the electric fleet? Don't we have to improve the diesel fleet as well? So it's that technology divergence is one of the issues. So that's the problem. We're going to give you some solutions. First of all, I'm going to hand over to my colleague Markus, who's going to introduce Danfoss, Danfoss's view in it, and then we're going to tell you what Danfoss can bring to the table as a solution. So, Markus.
Yeah, thank you, Niall. Next slide, please. Yeah, right. I want to tell you something about who is Danfoss and what is Danfoss doing. So, right. I mean, what we do actually, we engineer tomorrow, and we do we engineer solutions to enable the world to do more with less. And that does really mean that we are developing the right technologies in all areas when it comes to heating, cooling, drives and power solutions. To do more with less. That's what Danfoss is doing. And next slide, please. And we also have in Danfoss like a climate strategy, and this is quite ambitious and bold. And this does mean that we aim to become CO2 neutral by 2030. But also all Danfoss factories shall become CO2 neutral at latest by 2030, and all company cars should be electric by 2030. So there are also some ambitious goal Danfoss is setting for ourselves, and that's quite good. And the next slide. So what are the areas Danfoss is in right now? So we have 3 segments where we are active. One is Danfoss Power Solution, and that's actually the area where Niall and I'm working in. And that's so we are the mobile leader for mobile hydraulics for work machines, construction, ag machines, material handling, and so on, for hydraulics, but also electrification, complete solution provider. Then we have another segment called Climate Solution, and that's really coming down to heating and cooling solutions. And then we have Danfoss Drives as a segment, focusing on the power modules, on the drives, on the power conversion part. So these are the 3 segments. And as said, so really try to become efficient in all areas here. Focus on the energy efficiency. So when we now do one level deeper and do a deeper look into Danfoss Power Solutions, so we had like 2 billion sales and 7,500 people roughly in 2020, and this is the status of today. So we are active in the global world here, but as you might also heard from the news that we are acquiring Eaton Hydraulics, and therefore this does mean that our sales figures and our employees will change dramatically in short time. Our top markets are USA, Europe, and China. Next slide. And from a portfolio point of view, what Danfoss Power Solution is doing, so we are really the providing the core products, the solutions, the software to make all machines move on a propel part, on a traction part, but also work function part. And this in the end comes down to the core products like the pumps, the motors, the valves, the steering units, but also control areas like control units and software part. And there we also added since a couple of years now also the electrification portfolio, like motors, machines, converters, inverters, and also the digital displacement pump to make all those machines effective. So now I would like to spend a bit time on, we have a challenge as mentioned, and now we, how to reduce excavator CO2 emissions and give an outlook to 2030. So 400 megatons, mentioned by Niall as well. I mean, that's the global annual CO2 emissions by construction machines, so quite a big number. And if we now look down, I mean, what does it mean from a excavator point of view, production volume? On the left side, you can see that the annual production volume for excavators is increasing from today 600,000 machines up to 700,000 machines in 2030. And then if you look on the right side, that's a quite interesting picture that the split by smaller machines below 10 ton and the bigger machines above 10 ton is almost the same. So 44% for smaller machines and some more machines for the bigger machines. And that's how those machines are split today. But if you then look into how the CO2 emissions are accounting for these machine types, I mean, like then you can really see that the larger machines, the medium and large equipment is really contributing to a large amount of CO2 emissions. So that's what we are seeing. Next slide. And how to now really get down our CO2 emissions by 30% in 2030. We have done like an investigation, like a TCO calculation also, and we considered the average lifetime CO2 footprint for excavators produced in 2030. And we know that we need to reduce our CO2 emissions by 30%. We have considered our CO2 footprint, including manufacturing and operation phase. So the complete TCO from cradle to grave. And then we also included the carbon intensity of electricity supply. And in the end, what we found out, next slide, that in order to really achieve a 30% CO2 footprint reduction, so what should we do? If we just look into a focus segment of excavator and then just consider the 10 to 35 ton excavators, then we definitely need to look into machine efficiency to really make the efficiency, increase efficiency of the machine, but then also electrify. And this will contribute to the overall lower CO2 emissions. And this does mean we would need to increase the efficiency by 50%. Of 30% for 50% of the machines, and that's then in the end 150,000 excavators. But also we need to, on top of this, also electrify at least 40% of the excavators. And when doing this, then we could contribute to the 30% CO2 footprint reduction overall. So it's a quite ambitious goal, and this, to be done in 10 years. I think it's a quite ambitious goal, but I mean this should be done in order to get down the emissions. And where are we today? I mean, like if we just look on today's view, I think we can see a lot of machines electrified on the mini excavator side, so small machines. There we see a big movement and trend in the market. But if we then look into the medium duty and heavy duty excavators, in this case, like an example of a 25-ton excavator, we have done some TCO calculation, and what we are seeing that the conventional machine, so the machines today are definitely less cost intense compared to the battery electric vehicles, because this does mean that you have a lot of energy demand in the machine, and that does mean that you need to install a big battery pack in order to operate the machine during the duration of a day. And this does mean the machine becomes more expensive, and this is due to the battery cost today, but also the fuel price, which is today also at a low level. But if we then look into, and that's also the main reason why from a commercial point of view, the business case is commercially not viable, and therefore it's really driven by regulations, by incentives from governments and so on, that those machines also become electric. But if we then look into like the future state, next slide please, like a 5-year outlook, then we are seeing that we are seeing a trend in the market that battery costs are going down dramatically. We also see that fuel prices will go up due to government initiatives and regulations. And therefore we are seeing that even with today's comparing to today's machine to battery electric machines with conventional hydraulics in future, the difference is lower compared to today point of view. Therefore it becomes commercially more viable in 5 years just to electrify the machine and leaving the conventional hydraulics in there. But then there's also like a chance also to get like a lower TCO cost by also improving the whole machine architecture and not just electrifying, but also integrating the digital displacement hydraulics into the machine. And there we have a potential to really come down the cost of the conventional machine today. And that's really based on the lower battery cost and higher fuel price in 5 years. So there's a chance also commercially to make those machines attractive and to electrify and make hydraulics more efficiently, to also make them commercially viable. Next slide. And now we would have like the first question, and I mean this is now background shown by Niall, and the question to you would be, I mean, what fraction of new sales of UK construction equipment will be either battery electric or hydrogen fuel cell by 2030? I mean, what kind of what's on your roadmaps, and what do you see in the market as a trend? How many machines are converted from today's point of view in future? Maybe give you a minute or so to put some also answering in the chat. There's a chat function, I guess, in the Zoom meeting here, and if you want, you can put some estimates in.
Yeah, come on everybody, don't be shy. If anybody doesn't know where the chat box is, it's on the bottom line on the pop-up menu, and just click on the chat and put your estimate in.
So we are seeing 20%. That's already, I would say, quite ambitious target also. Very good. And it's really to be seen. I mean, like, there's the CO2 issue in the market, and therefore in our world, definitely, and therefore we must reduce CO2 emissions, and that's the way to I would say above 10 ton, you're right, 10 to 35 ton excavator. Because I mean, the smaller machines are, you can find so many, so many electrified already today. So there's trend towards more hydrogen. Interesting. 20% battery, 80% hydrogen. Thank you. Hey, this is good, and please continue to put in some notes here. I'm just while doing that, yeah, proceed here a little bit. Niall, maybe the next slide. So then let's spend a bit of time on the challenges on the machine level. So how to maximize the efficiency, productivity, while minimizing TCO. If we look into the complete chain from energy source up to productive work, we are seeing that we have a lot of losses in the system. So we are just using 30% of the diesel out of the engine output, and then we have the working hydraulics, which is also an inefficient system because the product at the system level is not super efficient, and therefore we just in the end use 12% of the input energy source, which is diesel, for productive work, and therefore we have a lot of losses, like 88% in the whole system. And that's what we see today in these conventional today's machines. If we then look into what can we do, next slide. As first step, we can definitely replace the engine as a first step. And this does mean that we are changing energy source from diesel to battery or hydrogen as one example. And then we have the electric drive system using as the prime mover, so to say. And then we can utilize 90% of the input energy source for driving the hydraulic circuit. And then we still have the conventional hydraulic system, and therefore we have a lot of losses in that system, and therefore we can use 27% for productive work, which is still a lot of losses in the system, but we are seeing definitely that it's a big increase from 12 to 27, so it's 50% higher efficiency and more productive work, and that's one enabler to start with, to really electrify and utilize the technology. Next slide. And just, I mean, Danfoss has a new division also in that area, and just short here, one picture about the Editron system portfolio, and that's really, all machines, I mean, for traction, for generators, then we have electric converters to drive a motor, to make a DC-DC conversion, to make a grid connection even, so you can connect like a stationary machine to the grid also, there's possibility also. And the complete system is designed for off-highway and for rough environments. It's really super compact, robust, and highly efficient. And that's optimized for these machines. And the next slide. And to show you one also example, we have in Norway, which is the one country which is known also for the regulations. I mean, pushing down the limits and also bring in those electrified machines and cars quite fast. And there are those excavators now also working in Oslo, in the city of Norway, which is fully electrified. And this machine was an easy swap of the ICE. So the engine was put out, and then there was a big battery pack put in, and our Editron system to power this machine. So it's a full electric machine operating also in Oslo, in Norway, and now more and more machines are produced of that type. Next slide. And now I think Niall will take over again and just explain the next steps. I think we have now talked about the first step to replace the energy source and bring in the electric system, and now we focus on the hydraulic side.
Yeah, thanks, Markus. So talking about the hydraulic system, let's look at the conventional technology of today. So we have what I call analog hydraulics. So here is an animation of a typical axial piston swash plate pump, as would be found as the heart of the hydraulic system of a typical excavator today. And that machine is controlled by varying the stroke of the pistons. So it's basically an analog mechanism. And that leads to a limited energy efficiency potential of this type of component. But also, because it only has a single controllable outlet, typically, It means that to control all the multiple actuators of an excavator, you need valves in between. And valves basically work by wasting energy. That's how they work, they throttle. And so because of that system architecture, basically the excavator system inherently is going to be of low efficiency. And lastly, these analog pumps, they're rather difficult to control by computer because they are fundamentally analog mechanisms. And to interface them to a computer, you need a lot of signal conversions and extra complexity. And ultimately, they're still analog at heart. So we introduce the Danfoss portfolio technology to solve these problems called digital displacement. So it's a fundamental reboot of hydraulic pump technology. It's a radial piston machine controlled by enabling and disabling cylinders in real time. So that's a purely digital process. There's no variable mechanisms or proportional analog mechanisms in the system. And that's done by using computer-controlled valves. So this is basically a software-controlled machine. And that brings many advantages at the system level, including higher efficiency, better control of the engine or the prime mover, and it basically behaves like an electrical inverter from the system level. So it's the hydraulic pump that electrical engineers love. So the advantages of that, much better component efficiency. So typical between a third to a fifth of the losses of the axial piston pump. So a real dramatic cut in the amount of energy wasted at the component level. But also because of these multiple outlets, it gives a much better system efficiency. And I'll show you the potential there just in a minute. And it has this digital control built in. So how we're getting this to the market is in a series of stages, because we're not talking about a revolution here. We're trying to describe what we would call a green evolution. So that means that step by step, we can introduce the technology and make incremental improvements and also establish a baseline and establish familiarity in the market, in service, in designers and in end users with this new technology. So we start off with what we call SA1, System Architecture 1. That's simply swapping the analog pump out and putting in a digital pump. That can also give some benefits in terms of control. So it can actually, as well as improving efficiency, it can also improve the productivity of the machine, which of course, improving efficiency saves fuel, and that's money, but improving the productivity saves time, and that's also money. So if we go the next level up, we can start to use some of the features of digital displacement to reduce the losses in the valve block. And this is what we call the SE2. We make use of these multiple independent outlets to redesign the hydraulic circuit. We still typically have proportional valves to control the actuators, but we change how those proportional valves are supplied from the pump, and we reduce some of the system losses. And then moving on up to the future, and what we're working on in the lab at the moment, and we're expecting to make it to the market in the 5 to 10 year region, is what we call SA3, where we eliminate completely the losses in the proportional valve. We control every actuator directly from the pump. And that also allows us to start to recover energy that would otherwise be wasted in, for instance, lowering the boom or in swing. So in terms of our development status and commercialization status of these three different levels, in SE1, we've demonstrated recently about 15% fuel savings on a modern excavator and 15 to 20% productivity improvement. And those fuel savings are gained even if you're doing a hard digging cycle or if you're doing a cycle that involves a lot of swing. So this is not like the electric hybrid systems that we've seen, which really are very sensitive to the duty cycle. This is a sort of across the board 15% that we can expect here. So we've done proof of concept. This was back about 2016. We did those demonstrations. We've taken the lessons there to productize the product. The first product that we've taken to market, which is called the DDP 096 Tandem, and you can see it behind me in all its beauty. That product has been taken to customer trials, and we're now in the sales phase, and we're getting lots of excitement and lots of engagement there. We look at the SE2. Here we've demonstrated over 30% fuel savings compared with that baseline system, and 20 to 20%, 25% productivity improvements. Again, you waste less energy, there's more useful energy to do work, and that can really turbocharge the machine from the operator's point of view. So there we've done a demonstration there. We published the results there towards the end of last year with a paper, and we've taken those results, we've created a productized version, which we're now demonstrating to some OEM partners that we're working with to put that product into their machines and demonstrate it at their facilities. And those projects are going very well, already starting to get very exciting results back from those projects. Then we look to the future and the SE3 architecture. So here we think we can get up to 50% fuel savings. Again, that's by reducing the losses, but also by recovering energy from the system. And of course, again, huge productivity savings are possible there. And there, we're at full scale in the lab, demonstrating the elements of this technology in a sort of building block way. So we've demonstrated recently very efficient energy recovery. And we're working on a new pump called the DD180, which will be a much bigger pump suitable for the 25, 30 ton excavators range. And this machine is designed from the ground up to have these multiple outlets to enable these more advanced systems, and indeed to enable energy recovery. And that machine is now undergoing tests in our laboratory. We're going to be benchmarking it against conventional analog pumps towards the end of this year. And yeah, we're already working with a number of OEMs and sharing the excitement of that and the interim results that we're getting as we're getting them. And that is just supported by the Advanced Propulsion Centre in the UK. We're very grateful for that support. This has been fantastic. And indeed, that support of the APC has encouraged Danfoss to invest further into its footprint in the UK, and a very recent announcement that there'll be a new building in the Edinburgh area, which is a low carbon innovation centre, which will house both digital displacement and Editron engineers working on low carbon innovations. So fantastic that we got that support, and that it's encouraged Danfoss to make a real permanent footprint in the UK. So what we've been working on in the lab quite recently is a demonstration combining what we say the most efficient electric motor and inverter system from Editron, of course, with what we say the most efficient hydraulic pump, the digital displacement pump, combining those together to really see how efficiently can we convert DC power from a battery into fluid power that, of course, can make an actuator move. And these are some results we've had quite recently. 87% efficiency overall from DC battery power to fluid power at 100% load. 83% at low power, but these are very high numbers, and we think that this is by far the most efficient way that exists with current technology to turn battery power, or let's say fuel cell power, into fluid power to work hydraulic actuators. And so very encouraged by these results. So again, looking at the challenge that we discussed earlier on in this presentation, the barriers to electrification. So we can see that if we improve the system efficiency using new technologies, then we can reduce the size of the battery that's required. So less energy wasted means you have a smaller battery. That improves the initial cost of the excavator, of course, and of course it means that with a limited supply of lithium or manufacturing of cells, then you can actually electrify far more of these heavy machines. And secondly, of course, if you've got a smaller battery, then you need less charging power overnight at your work site. And of course, that's a major limitation, as we've noted. And therefore, yeah, it could be that you could get way more machines on a typical work site with the given limited charging infrastructure that's there, just by reducing the amount of waste. And then lastly, limited green energy on the grid. Well, if we need less charging energy, we're wasting less of that precious green energy, then of course that really helps. It means we can make much more impact in terms of CO2 reduction for a given amount of green energy investment. And so that's a real multiplier on some of the other actions that government's taking to, of course, incentivize the production of that green energy in the first place. So really we see it as a two-pronged approach here. We need more green energy, but we also need to make sure that green energy is not wasted. And so green energy should power, green machines, which are highly efficient. And this last point here, I think, want to emphasize this. What we're proposing here is to improve efficiency with a technology which is shared between the diesel and the electric variants. So the power of that is that in the short, medium term, of course, diesel will dominate the market, especially in the larger machines. So by improving the system efficiency with this technology, we can make a big impact on CO2 in that short and medium term. But also by improving system efficiency, we can see we lower the barriers to electrification. So we also see that that improved system efficiency will accelerate electrification. So it's a double act, if you like, of efficiency helping in the short term, but also helping accelerate that electrification. And one way we can think about looking at it, maybe from the government or the regulator's point of view, is today it seems that incentivizing electrification is like pushing a rock uphill, because what's forcing the rock down the hill is market forces. As Markus has said, today electrifying off-highway machines is much more expensive, and so it's much more difficult to persuade end users and operators to adopt this technology in the presence of such a strong market force against it. And what we want to do by lowering the cost of electrification, by improving efficiency, is get to this situation where it's a runaway. We reach the tipping point where electrification is actually cheaper. As Markus has shown, we can get towards that TCO advantage for electrification until actually electrification works simply on a straight business case. And we think that's when the takeoff point will be. And getting towards that tipping point, we believe system efficiency is the key to get to that tipping point. So yeah, in summary, and thanks for your attention. Hope you've enjoyed our presentations today. I just want to come up with some final thoughts of the way ahead and summarize some of this. So underpinned by this theme of improved efficiency, we think, first of all, we have to tackle that efficiency on the diesel fleet, which will be the majority of the emissions for the foreseeable future. And that has a synergy with the electrification. It will accelerate electrification if we can improve the efficiency and get to that TCO tipping point sooner. And so we've got some talking points really to think about here, maybe for regulators and governments, as they're thinking, how do we get the right behaviours from the industry? What incentives do we put in place? What regulations do we put in place? Well, I would just say, first of all, recognise the issue of system efficiency. It's the low-hanging fruit. So there's massive potential to reduce the CO2 of today's diesel machines by improving system efficiency. And so that means when designing the incentives and the regulatory scheme, think about incentivizing improved system efficiency and see that as a first step towards the electrification of these machines. And then lastly, address some of the limiting factors for electrification. For instance, electric charging infrastructure. I'm sure there's a lot that could be done there to improve that where the machines are actually used. And then, for the OEMs, you maybe also have an agenda to talk about. One thing I think has been really powerful is the science-based targets commitments. And we've actually found that some OEMs have come to us specifically because their organization has, from the top down, committed to this stretching target to reduce CO2 of their machines in use. And their R&D people have come to us saying, we need to look outside of our own organization now. Because we have this stretching target, it's changed the game. It's no longer about incremental improvement and perhaps doing that in secret. It's actually about open innovation. It's about going out to the whole world and finding out what the best technologies and making partnerships with companies, organizations that are working on solutions. So another thing that we can do is maybe cooperate on standard test cycles. This is something that in other markets makes it very easy for a consumer to select the most efficient technology, but unfortunately in off-highway machines it's much more difficult, and you could say a lot of that information is not available. So that would be maybe one step that could help, allowing end users to access to the information, either from standard test cycles or from telematics to know, which are the most efficient models. And then lastly, to OEMs, think about the efficiency of your hydraulic system and think about that as a common element between both diesel and electric variants. Okay, so thanks for your time. Still got a little bit of time left for some Q&A. Now you can ask what you like. Ask about the technology, ask about Danfoss, ask about the view on CO2. Just got some stimulating question up here. What are the major obstacles to reducing construction machine emissions by 2030? How do you see it? Is it the battery supply? Is it that infrastructure? Is it something maybe we haven't talked about, like for instance the need to train all the customers how to service these electric machines safely? We'd like to hear from you, and definitely at this phase Danfoss is in a listening mode. We've done this study of the outlook to 2030. We know that Danfoss doesn't have all the answers, and that actually Danfoss can't even make the improvement or provide the solution without a partnership with OEMs, with end users, with operators, and indeed with government to get a way forward that we can work together and cooperate. So we're really listening. We want to hear what the industry has to say and how we react to what we have to say here. So very keen to see your questions, and myself and Markus will be happy to answer your questions. Okay, so thank you.
Thanks very much indeed for that, Niall and Markus. That was very good. Thank you for all of that information. So there are 22 participants on board. We would normally ask for questions to come in via the chat. There is one on green H2 at the moment, green hydrogen, on the chat, which has been partially answered. Sorry, Niall, I approached that from the wrong angle. I understand your question now. So if you guys could have a look at that one, and also I actually had but please feel free to raise them directly, just vocally, because I think there's enough of us on here to control the questions through verbal means.
Yeah, sure. Yeah, please unmute and just ask your question if you've got one, and let's have a conversation. There's still a bit of time left in the schedule, so yeah, happy to talk to you.
Maybe while people are thinking of their questions, guys, there was one that I was going to ask, and actually you partially covered it on the last slide anyway, and it was really about inhibitors. We heard lots of good reasons for a change in technology, but there's always conservatism about making a change, and I just wondered about your view on where those obstacles in conservatism might lie. I mean, is it with manufacturers? Are manufacturers reluctant to adopt the new technology and make the change? Is it perhaps with the customer base? Is there maybe a reluctance from customers because these are their workhorses, these are their money earners, to switch to a technology that is unknown and untrusted? I just wondered, obviously from a personal view, from a relatively small experience, I just wondered what your view was on that.
Yeah, Markus, would you like to lead off on that?
Maybe I can start. Yeah, I think maybe my personal take on this, I think it's all about risk reduction on the OEM side. And I think if we talk about the big technology step change, I think then I think there might be also risk associated to that, and therefore it's so what we are hearing from customers, from OEMs also, that they want to see evidence. So really, what have we done? And therefore we also have our application development centers where we have machines really on the centers, and we can convert technologies from conventional to new technologies, and then we can also demonstrate, and then OEMs and end users can test our machines and then really see that performance is increased and efficiency is improved, and these kind of things help a lot to really break down barriers and to mitigate the risk, I would say.
Yeah. Yeah, I would say from my side, I think one of the challenges is, let's say, a divergence of outlooks of different companies, different routes towards that low emission future. Perhaps some companies are pursuing hydrogen. Some even, I heard from JCB the other day, looking at hydrogen in a combustion engine. And then we have some companies very strongly into electrifications, and others working on the hydraulic system efficiency issues with hydraulic hybrid, for instance. So there's a real fragmentation, if you like. And I think what we're trying to do here with digital displacement is try to make it what we call a no regrets option. In other words, if we improve the system efficiency of these machines, perhaps 5% will be electrified, 10%, 15%, but you'll stay with a common heart, a common technology. You'll be able to concentrate your resources onto that, and that technology will then go with you as you electrify, or indeed as you make with hydrogen. So I think that's maybe part of the solution that we're trying to offer, to minimize the amount of divergence and the sheer number of different technical solutions, to try and concentrate that on one. But in terms of the limiting steps, I think it's unfamiliarity, and as Markus has said, risk is a huge issue in this market, and that's why we've been working for the last 5 years on a lot of validation, a lot of testing, extreme conditions, extreme speeds and pressures and oil conditions and so on. And this is the sort of information that we share with the OEMs when we get into that deep discussion. But it's also, even if you have that data, OEMs typically want a demonstration, and they want to see it with their own eyes and with their own, measurement devices, which absolutely correct. And so there is a certain rate at which we can work at, and there, what we're leveraging now is the power of Danfoss's application development centers worldwide. And we're spending a lot of time now on training internally as well as externally, so that we get more and more people on the Danfoss side who can work with OEMs on the application engineering of digital displacement in their systems. So it's that scaling up and working on multiple fronts, I think, is one of the big challenges.
Yeah, interesting. You both used the word demonstration in your answers, and certainly from my point of view, I would imagine that demonstrating the technology and the benefits of the technology will be a huge gain in terms of manufacturers and customers gaining confidence in the reliability, the robustness, and the payback, the benefits of the system. So certainly, yeah, that would be a good, a very positive step as far as I'm concerned. I don't know if you guys. Oh, sorry. Yeah.
Hi, Neil. Neil Davidson here. I don't
know.
Neil. Hi. I don't know if you hear me okay. Just the differential tracks treatment of red diesel is obviously going to change next year. So red diesel is going to become more expensive. Do you think that could result in a shift from sort of end users, consumers, purchasers of machinery, where better efficiency will sort of move higher up their consideration of purchasing or renting machinery, that actually the operational costs are going to be a much bigger component of the total cost of ownership, and then there might be some kind of tipping point where efficiency becomes the new flavor, possibly?
Yeah, from my view, I think we can see it's like an imminent occurrence in this country, is a sudden dramatic increase in the fuel cost. And I'll be interested to see. It's a big experiment, you could say, the industry is being subjected to. We'll see how it responds. But I think the difficulty from the customer point of view is knowing any type of comparable figures from OEMs, or getting some sort of prediction if they buy a new machine and they invest in that new, more efficient machine, just how much energy are they going to save. And so there, I think some open sharing of information, some standardization could be useful. I'm just like everybody else, keen to see how the market reacts to that sudden increase in fuel cost, and maybe there's some other perspectives on the call here.
That's a good point you raised, Neil, because there will be a step change in fuel costs. We're used to fluctuations in fuel costs, but there will be a step change next April when that red diesel rebate goes. Already total cost of ownership is dominated, or certainly a significant factor in TCO is fuel cost, depending on the machine type. And that step change, I think, could have a dramatic effect in bringing about a change in attitude towards machine efficiency. So no, you raise a very good point there. I see we're at actually just a little over the hour. We normally do go on just slightly over the hour, so apologies, we've done it again. But any final questions from anybody from the floor before I hand back to Joanna?
I could maybe just make one comment about the hydrogen. It has come up, and we didn't really cover it in our presentation. That's partly because we're focused on the 2030. You can see, from the chat, some people think it will make a big contribution by 2030. But I think it's clear to us that we talk about green hydrogen. There's a limited amount of it, and we can only make so much because the same offshore wind turbine that makes the green hydrogen could be connected to grids and decarbonize the grids that way. But there's also a never lengthening queue of industries that are looking to use that green hydrogen to decarbonize. The airline industry, for instance, they're queuing up to use that green hydrogen. On-road trucks, it's widely seen as the route for very heavy trucks that do long distances. And I saw just a couple of days ago Formula One saying that they're going to start running their cars on green hydrogen as well. So there's a never lengthening queue waiting to get access to that green hydrogen, and I think you have to question if it's going to make a significant impact by 2030 in this industry when there's a queue of other very hungry consumers for that green hydrogen, perhaps in front of the construction industry. Yeah. Okay. That was my final point from me, but I just wanted to say thanks so much for this opportunity. It was a real pleasure to get this opportunity to share our insights, and we'd like to continue this conversation. And please come along to some other engagement events we're doing as Danfoss, or reach out to us individually, and it'd be lovely to carry on this conversation and see what else we can do with digital displacement. So thank you very much for that.
Thanks so much, guys. There is actually one last question that's gone in the chat, so I don't know if you're able to copy and paste that into another forum, and then maybe answer it offline. But there's one last question there. So thank you very much indeed once more, and I'll hand you back to Joanna.
Okay, thanks very much, Dale, and thanks very much, Neil and Markus. That was a really great deep dive into quite a technical subject, and I know that you both said you'll take questions offline, so we can put anybody in touch with you afterwards, and I hope it's something we can return to when we start looking at CEA technical days, and linking that in with PlantWorks, which we're looking to do in the next year when we haven't got our PlantWorks exhibition in full. So just a quick advert for the next power hour. We try and switch in between technical and exports or sales. So the next power hour will be on the 25th of August. We have two speakers from Midlands Engine, which is a government body looking after manufacturing in the Midlands. We have Anya Novak, who I think many of you will know, and her counterpart in the West Midlands, Marion Doherty, and they're going to be looking at how they can help you export, not just actually going places, but preparing for it, researching it, what support there is out there, and how they can help link you in with contacts in your chosen market. So thanks, everybody, and that's all, folks. See you again next month, and enjoy the sunshine while it lasts.